In the boundless depths of deep space, thousands of light years from Earth, amid brilliant stars and clouds of dark dust, two mysterious celestial bodies orbit each other, defying the classical laws of physics. The echoes of their motions reach us across thousands of light years, even though the bodies themselves are incredibly small by the standards of the universe. The surrounding space is distorted, forcing even the most unstoppable photons to deviate from their predetermined trajectories. The flight of these objects is so rapid that time slows down for them, and titanic tidal forces crumple their surfaces, covering them with folds and cracks. It's a rare and astonishing sight, even by the standards of the infinite universe. Let's take a closer look. 3,200 light-years from Earth, the constellation Papas, a distant past. The lives of two red giants are coming to an end. Before our eyes, one of them is entering a new phase of stellar evolution. Its internal fuel is nearly exhausted, and the star is beginning to cool rapidly. The delicate balance between the force of gravity and the fury of a thermonuclear explosion is irreversibly altered. Trillions of tons of stellar matter begin to be drawn inexorably toward the star's center. This process triggers a new runaway thermonuclear fusion reaction within the star. The powerful explosion tears the star apart, leaving behind a super-dense core, incandescent at incredible temperatures. The force of the shockwave irreversibly alters the structure of the stellar matter, completely destroying its atoms. These are compressed into super-dense matter, generating countless neutrinos. In place of the destroyed giant, a tiny but extremely massive clump of matter remains. Around it, the outer layers of the former star explode into a huge cloud, transforming into a nebula of scattered gas. These collide with another nearby red giant at great speed. This causes this other star to ignite like its companion, which has just ceased to exist. And when the echoes of the double supernova dissipate into space, only a pair of mysterious objects remain, almost invisible in the vast void of space. This is how a great catastrophe produces extremely rare and unusual cosmic objects, which we call neutron stars. Currently, only a few thousand celestial bodies of this class have been discovered, a tiny number compared to ordinary stars. And to understand why they are so rare, we must study the evolutionary paths of stars. According to current concepts, the life of any star is determined almost exclusively by its mass. With a mass less than 8 solar masses, a star, after completing several evolutionary stages, transforms into a white dwarf. It is assumed that after billions of years it will lose the rest of its energy and transform into a hypothetical object called a black dwarf. This path is destined for over 99% of the stars in the universe, including our Sun. If a star's mass exceeds 8 solar masses, however, its evolution follows a different path, ultimately leading to a supernova explosion. The star's outer shells disperse into the surrounding space, forming a nebula of diffuse gas. At the center of the system, a super-compact and extremely dense object remains, the former stellar core. If the mass of the stellar remnant is between 1.4 and 2.2 solar masses, a neutron star forms. The gravitational forces within it destroy atomic nuclei, forming superdense neutron matter with rather bizarre physical properties. For a variety of reasons, neutron stars are extremely difficult to observe and study. Therefore, before the advent of X-ray telescopes, these objects were impossible to detect. It's no surprise that the first neutron star was discovered only in 1967, several decades after their existence was theoretically justified. This is largely due to an unusual phenomenon associated with the law of conservation of momentum. Thanks to this effect, most neutron stars rotate very rapidly, and the interaction of their magnetic and electric fields generates powerful bursts of radiation, repeated with very precise periodicity. These objects are called pulsars and constitute the majority of neutron stars discovered so far. Their pulses are effectively detected by X-ray telescopes, even at distances of thousands of light years. In total, more than 3,200 neutron stars have been discovered so far, about 90% of which are single objects. The remainder are part of binary and multiple star systems. Most often, the companion of these cosmic bodies is a red giant or a main sequence star, but in isolated cases, another neutron star can also be found. This happens when two similar stars approach each other in synchrony at the end of their life cycles, and the explosion of one triggers the collapse of the other. Due to the loss of energy during this transformation, the remnants of the stellar cores converge tightly, causing their relative velocities to reach enormous values. And according to current theories, this is how the extraordinary system called PSR J07373039 was formed. It is located approximately 4,500 light-years from Earth and is quite unique, consisting of two pulsars very close to each other. The first of these is 34% more massive than the Sun and has an incredible rotation speed. Every second, the object completes 44 revolutions around its axis. The second pulsar is a little smaller and slower. Its mass is 1.25 times that of the Sun, and its rotation period is 2.77 seconds. If we look more closely at these objects, we'll see that they are extremely small by space standards. Both components of the system are no more than a few dozen kilometers in diameter. Their mass is actually comparable to that of most known stars. Because of these factors, the density of the matter composing pulsars is extremely high. And to understand this question, we need to look inside them. The use of mathematical modeling techniques, combined with the theory of neutron star structure, allows us to understand even aspects that aren't immediately visible. The outermost layer of objects of this class is the atmosphere. Incidentally, however, for neutron stars, this concept differs significantly from the familiar sphere of gas that envelops a planet, such as Venus or Earth. For both components of the system we are now observing, this layer is no more than a few millimeters thick. This situation is typical of the vast majority of neutron stars. But the youngest and hottest objects in this class can have atmospheres several tens of centimeters thick. They are composed of plasma, the highly ionized remains of stellar matter. Most of it consists of hydrogen and helium atoms, but heavier elements are also found. The next layer is the outer crust, which can reach several hundred meters thick. Gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, but it is strong enough to disrupt the usual structure of matter. The elementary particles are all mixed together but still maintain their internal integrity. Several powerful forces simultaneously exert pressure on the outer crust, including gravity, magnetic fields, electrostatic repulsion, and centrifugal inertia. This combination subjects the surface of neutron stars to constant mechanical stress. Occasionally, this stress builds to the point where stellar quakes occur, causing massive deformations of the cosmic object's surface. As a result, mountains a few millimeters high and cracks up to a centimeter wide form. These numbers seem insignificant, but under extremely high gravity, a centimeter-high mountain is comparable to Mount Olympus on Mars. If we delve even deeper, we'll see that this layer has no clear boundaries and extends several kilometers deep into the neutron star. As we dive deeper into its interior, the pressure gradually increases, pushing more and more electrons toward the atomic nuclei, triggering a reaction with the protons. This results in the formation of a neutron, as well as a highly elusive particle called a neutrino, which almost immediately leaves the interior of the celestial body, taking the excess energy with it. In turn, beneath the inner crust lies the outer core, composed entirely of neutron matter. This extraordinary substance consists of a multitude of tightly compressed neutrons, whose density is 10 to 15 times greater than that of the atomic nucleus. For example, our planet, compressed to the same degree, would have a radius of only 150 meters, and 1 cubic centimeter of its volume would contain several billion tons of neutron matter. In both components of the system we are observing, the outer core extends to the center of the object. Incidentally, according to current concepts, even particularly massive neutron stars should have an inner core. Its structure is still a matter of scientific debate. According to one hypothesis, the pressure at the center of massive stars may be so high that it can even destroy neutrons, forming a hypothetical quark matter. Such an object is called a quark star. Other hypotheses suggest the formation of hyperonic or kaonic nuclei, composed of bizarre matter with extremely unusual properties. However, all these surprising structures remain hypothetical, and their existence cannot yet be proven or disproved. If we look at the system as a whole, we discover several surprising and intriguing facts. First, we can note that, according to calculations, the pulsars in this system move rapidly around a common center of mass along moderately elongated and very compact orbits. Observations show that the average distance between the components is only 800,000 kilometers, or almost half the diameter of the Sun. Because of this small distance, the velocity of the two objects' relative motion is very high. It exceeds 300 kilometers per second, so the pulsars complete a complete revolution around a common center of mass in just 2.45 hours. Such rapid motion causes a series of unusual phenomena due to effects explained by the theory of relativity. For example, observations show that at the moment of maximum pulsar convergence, the rotation period of each pulsar temporarily increases by 0.38 microseconds before returning to its previous value. Although this effect cannot be explained from the perspective of classical physics, the theory of relativity predicted it long before its practical detection. This anomaly is associated with relativistic time dilation, which reaches its maximum value precisely at the moment of maximum convergence of the objects. Within a year, it shifts from its previous position by up to 17 degrees. Therefore, PS J0737-3D03D9 exhibits the highest relativistic shift of any known star system. If we leave aside the dry numbers for a moment and consider the hypothetical planets that might be lurking in this extraordinary system, their existence seems rather unlikely but still possible. Some objects far from the center may have survived the double supernova explosion, while others may have formed later. This question is even more difficult to answer because none of the methods used to search for other diffuse planets are effective for exploring such systems. In any case, we cannot speak to the viability of the hypothetical celestial bodies in the system. So if you enjoyed the result, let us know in the comments. Don't hesitate to leave us your sincere likes, and new informative episodes will be coming soon. And let's stay connected.